Welcome to CyberEd's presentation of electronic structure. This program will define the electron's role in atomic structure, show how the electronic structure of an atom has been determined through experimental investigation, discuss the roles of quantum theory and quantum mechanics in our understanding of the organization of electrons within an atom, and organize the elements into a periodic table. To a chemist, electrons are everything. The number and arrangement of electrons determine the chemical properties of an element. The ease with which an element gains and loses electrons determines which elements combine to form compounds. Electrons are more than just chemistry, though. The movement of electrons powers our machinery, and the controlled transfer of electrons runs our computers. The colors that we see are due to shifting of electrons within atoms. In fact, the very fabric of life itself is tied to an organism's ability to use electrons in converting food into energy, transmitting sensations to the brain, and bonding proteins together during cell replication. We distinguish one element from another on the basis of its atomic number, the number of positively charged protons that each atom of the element contains in its nucleus. Since atoms are electrically neutral, there must be the same number of negatively charged electrons surrounding the nucleus as there are positively charged protons within the nucleus. In this program, we will look at the arrangement of those electrons, both as determined experimentally and as predicted by quantum theory and quantum mechanics. In 1896, J. Thomson discovered the electron and demonstrated that it was part of the atom. In the early 1900s, the physicist Ernest Rutherford demonstrated that the atom is composed of a dense, positive core, or nucleus, circled by a set of negative electrons. Immediately, scientists were puzzled by the fact that the negative electrons were not attracted to the positive nucleus, but instead remained in orbit around it. This problem was addressed by Niels Bohr in 1913, using earlier observations on electron behavior by Max Planck and Albert Einstein. The result was the quantum theory of the nuclear atom. The model of the atom based on quantum theory is often called the Bohr atom. Bohr stated that as long as the electron moves with a certain minimum speed and stays in a certain fixed orbit, the electron will not be sucked into the nucleus. You might compare this to your spinning a light stick on a string around your head. As long as the light stick keeps moving above a certain speed, the string stays taut. But if the light stick slows down, it drops out of its orbit onto your head. We've been talking about electronic orbits as if we could see them, which is impossible. Our pictures are drawn from inferences based on experimental evidence and mathematical calculations. What we can see, however, are the traces of light emitted by electrons making the transition from an outer orbit to an inner orbit. An electron in an outer orbit needs more energy to remain in its orbit than does an electron in an inner orbit. Think about the light stick on a longer string and how you have to spin it faster to keep the string taut. So the transition by an electron from an outer to an inner orbit involves a change in its energy. The energy lost by the electron during its transition from an outer to an inner orbit is emitted as a flash of light, called a photon. An interesting example of this useful phenomenon is the laser, where energy is supplied to the atoms to pump up or excite the electrons into a higher orbit. The photons are emitted when the electrons give up that extra energy and return to their usual lower orbit. Fluorescent lights, neon signs, and the monitor on which you are viewing this program all use the same principle to provide emitted light. The light that is emitted when an electron drops from a higher to a lower orbit is part of the electromagnetic spectrum, which is the measure of the radiant energy that exists in our world. The radiant energy we are most familiar with is the visible spectrum, which is represented by the colors of the rainbow. But the non-visible microwaves, radio and television signals, and X-rays are other segments of the electromagnetic spectrum which you deal with in your daily life. In the electromagnetic spectrum, we represent radiant energy as waves. Waves can be characterized by their wavelength, which is the distance in meters from one wave crest to the next, or by their frequency, which is the number of waves or cycles per second. Since the speed of light for any portion of the electromagnetic spectrum is 3 times 10 to the 8th meters per second, it is possible to calculate wavelength from frequency and vice versa. Using a device called a spectroscope, it is possible to measure the exact frequency or wavelength of the light emitted when an electron changes levels. Spectroscopic measurements were being made in the 1890s, well before the concept of the electron had been developed. It was obvious that the emitted light resulted from some internal transition within the atom. This led Max Planck to state, in 1900, that the frequency of that light is a measure of the amount of energy that was emitted during the transition. The mathematical factor relating the transition energy and the frequency of the light is called Planck's constant and is abbreviated h. About 5 years following Planck's relating transition energy to the frequency of the emitted light, Albert Einstein observed that the ejection of electrons when light struck a metal, called the photoelectric effect, required a particular amount, or quantum, of energy. The frequency of light that caused electron ejection and the related amount of energy of that ejected electron varied from metal to metal. This was, in essence, the reverse of spectroscopic observations of light emission. Instead of electronic transitions producing light, light produced electronic transitions. Einstein even used Planck's equation, E equals h times nu, to quantify his results. About 8 years after Einstein's observation regarding quantized energy, Niels Bohr proposed that electrons circled the atom in orbits that corresponded to varying amounts of energy. He further suggested that there was a minimal amount of energy needed to keep the electron stable in its lowest orbit, and the energy being emitted during a transition from one orbit to another was exactly the amount that the electron needed to lose to remain stable in the lower energy orbit. This idea of fixed energy values, or quanta, led Bohr to conclude that the electron could only occupy fixed or discrete energy levels, called quantum levels, and he proposed an energy diagram in which the physical distance of the electron from the nucleus was represented by these levels. This Bohr model of the hydrogen atom was the first application of what is called quantum theory to electronic structure. Although quantum theory did a great job of explaining hydrogen, spectrographic evidence for elements other than hydrogen indicated that there were many more electronic transitions observable than could be accounted for by only the 7 quantum levels proposed by Bohr. Transition energies were seen in other elements that could only be explained by assuming that the levels postulated by Bohr were divided into sublevels. In particular, analysis of the transitions for neon showed that spectra associated with the higher levels could be characterized as falling into 4 separate categories: sharp, principal, diffuse, and fundamental, abbreviated as S, P, D, and F. The S, P, D, and F spectral features suggested that the quantum theory, which explained electrons traveling around the atom in orbits at fixed distances from the nucleus, needed to be modified to provide a more complete explanation for elements other than hydrogen. The different spectral features implied that the 7 different energy levels proposed in the Bohr model showed variations, electrons appeared to be able to travel around the nucleus in more than just 7 distinct levels. Thus arose a need for a more complete theory that explained the sharp, principal, diffuse, and fundamental series of spectral features. Obviously, the quantum theory concept of electrons with fixed energy moving in circular orbits that were separated by a quantum of energy from other orbits, which had worked so well to explain hydrogen, needed some refinement if it were to explain these spectroscopic observations on other elements. In 1925, Erwin Schrödinger developed a major breakthrough in the understanding of electronic structure, a mathematical treatment called quantum mechanics, which permitted the calculation of the quantum energy value for each individual electron in any atom. Quantum mechanics accounted for the levels concept of quantum theory, and it also explained the S, P, D, and F sublevels and their subdivisions, which Schrödinger called orbitals. Quantum mechanics also showed how each of these sublevels and orbitals fit into a single energy diagram which completely described the electronic structure of any atom. According to mathematical descriptions provided by Schrödinger's quantum mechanics, the s orbitals are spherical. The p orbitals are 3 mutually perpendicular dumbbell shapes. The d orbitals are 4 orbitals of 4 lobes each, plus a 5th, then is like a p orbital inside a donut. And the f orbitals are extremely complex, but basically in 6-4 or 6-lobed patterns with a 7th orbital that looks like a p orbital with a bow tie. Quantum mechanics also changes Bohr's concept of electrons as particles moving in fixed paths. By recognizing that the electron can behave as radiant energy, like the photon, it can also be thought of as having wave-like properties similar to those you learned about in the discussion of the electromagnetic spectrum. Schrödinger formulated the orbital as a wave-like probability distribution. The electron will be found somewhere within the orbital, but we cannot state precisely where it is at any given time. This inability to pinpoint the electron is a result of an observation by Werner Heisenberg that it is impossible to know exactly both where an electron is, its location, and where it is going, its momentum, at any given time. His observation is called the Heisenberg uncertainty principle, and its mathematical formulation states that the product of the uncertainty in knowing the location and the uncertainty in knowing the momentum equals, somewhat surprisingly, our old friend, Planck's constant. The fact that light has both wave-like and particle-like properties, called the duality paradox, has been known to physicists since the early 1900s. The inclusion of the electron in this category, where it behaves simultaneously as a Thomsonian particle and as a quantum mechanical wave, illustrates that electrons have properties similar to components of the electromagnetic spectrum and can therefore show the same duality. In the electronic structures depicted in this program, we have chosen to depict the electron as a particle rather than a wave. Knowing full well that by pinpointing the location of the electron, we are violating the Heisenberg uncertainty principle. However, we will also show the orbitals calculated from quantum mechanics for the electrons, since the shape of the orbital influences electron behavior. Our purpose is to maintain clarity in depicting electron behavior, even at the expense of realism. Electrons have negative charges, and according to classical electrodynamics, they would be expected to repel one another if they were in the same orbital. Nevertheless, both experimental evidence and quantum mechanics demonstrate that there can be a maximum of 2 electrons in any of the individual orbitals. The justification for this fact was stated best by Pauli in 1925 as the Pauli exclusion principle. 2 electrons may occupy the same orbital if, and only if, they have opposite spins. Without getting into a lot of complex mathematics, we'll simply state that the spinning of the electrons on their axes in opposite directions offsets the repulsive effect. The opposite spins of the two electrons allow them to coexist within the same orbital. Even so, the repulsive nature of the electrons means that no orbital will contain two electrons until all of the orbitals at that sublevel have one electron. This is known as Hund's rule. The spin concept has been incorporated into quantum mechanics, combining it with Schrödinger's previous identification of level, sublevel, and orbital. We get the basic principle of quantum mechanics. An electron is completely and uniquely characterized by its level, sublevel, orbital, and spin. Spectroscopic observations show that the energy of an orbital increases with level number. The emitted light represents energy being lost as an electron moves from a higher to a lower level. Conversely, energy must be supplied to move an electron to a higher level. The shapes of the orbitals also play a role in sublevel energy. At any given level, the spherical s orbital is lower energy than the dumbbell-shaped p orbitals. The p orbitals are lower energy than the rosette-shaped d orbitals. And the d orbitals are lower energy than the f orbitals. As the level number increases, the energy differences between the levels become smaller, and the differences due to sublevel spacing become more significant than those due to level. As a result, the sublevels at the higher energy levels end up overlapping those from the lower energy levels. In particular, the 4s sublevel is lower energy than the 3d, but the 3d is lower energy than the 4p, so the 3d sublevel falls in between the 4s and 4p. The same effect is seen with the 5s and 5p sublevels being separated by the 4d, and the 6s and 6p sublevels are separated by both the 4f and the 5d. Similarly, both the 5f and the 6d sublevels separate the 7s and 7p. Combining all these considerations, we get the overall distribution of sublevels by energy level for all of the known elements. Now that you know how electron orbitals are structured, let's see what happens as we construct the first 36 elements of the periodic table. Recall that as we add protons to increase the atomic number, we must also add electrons to maintain electrical neutrality. The adding of the electrons, one by one, follows what is known as the Aufbau Principle. Aufbau is German for building up. The Aufbau Principle states that the next electron to be added will go to the open orbital with the lowest energy. Since each orbital at a given sublevel has essentially the same energy, electron repulsion and Hund's rule will ensure that no orbital gets two electrons until all orbitals at that sublevel have one electron. For example, neon, with 10 electrons, gets 2 in the 1s orbital, then 2 in the 2s orbital, then 1 into each of the 3 p orbitals, then a second electron into each p orbital. Building the first element is easy. Hydrogen, with its single proton, gets 1 electron in the first s orbital. Note that the orbital is spherical. Quantum mechanical probability calculations tell us that the electron can usually be found somewhere within a sphere whose radius is 5 times 10 to the minus 9 centimeters, or 0.05 nanometers. In the chemist's shorthand, the hydrogen electron is in a 1s1 orbital. Helium, with 2 protons, has 2 electrons. 1s2 in the chemist's shorthand, meaning that there are 2 electrons in the 1s orbital. These two electrons fill the first level, since it has only the s sublevel with its single s orbital. The orbital is still spherical, but now it contains two electrons with opposite spins. These two electrons, since they both have a negative charge, will always avoid each other. Beyond knowing that, the Heisenberg uncertainty principle doesn't allow us to say precisely where the electrons are at any given time. And remember that quantum theory requires that they must keep moving in order to stay in their orbital. With the first electron level now filled, lithium, with 3 protons, gets its third electron at the second level. This is a 2s electron, since the 2s sublevel is lower energy than the 2p sublevel. Note that both s orbitals are spherical, with the 2s orbital being larger than the 1s orbital you saw in hydrogen. Chemists would describe its electronic configuration as 1s2, 2s1. Since helium, with its two 1s electrons, represents a completed level, which is often called a closed shell, we can abbreviate 1s2 as the symbol for helium in brackets. We'll continue to use a new abbreviation each time we reach another closed shell. Beryllium, with 4 protons, has 2 electrons that fill the first level and 2 electrons that fill the s orbital of the second level. Can you see why the chemist would refer to beryllium's electron structure as 1s2, 2s2, or helium 2s2? Now we are ready to deal with the 2p sublevel. Each of the 3 2p orbitals can contain 2 electrons, so the 2p sublevel has a capacity for 6 electrons. As we add the next 3 electrons, we get boron, carbon, and nitrogen, with the notations as shown. Remember that the p orbitals aren't spherical. They are shaped like 3 dumbbells set at right angles to one another, with each dumbbell capable of holding 2 electrons. And also remember Hund's rule. Each orbital gets 1 electron before any orbital gets 2. As was pointed out previously, the orbitals being shown are just probability maps. The 3 orbitals for the p sublevel are usually referred to as the px, py, and pz orbitals. So if we wanted to be more explicit, we would symbolize nitrogen as 1s2, 2s2, 2px1, 2py1, 2pz1. Now let's complete the second level. Oxygen has the configuration 1s2, 2s2, 2p4. Fluorine is 1s2, 2s2, 2p5. And neon is 1s2, 2s2, 2p6. We've also shown electron configurations within the px, py, and pz orbitals on the screen. At this point, we've filled the second energy level and created neon, which is, like helium, a noble gas. That is, it is chemically unreactive. The reason behind this lack of reactivity lies in the favorable energy configuration of the closed shell. In general, the filling of the s and p sublevels with 8 electrons at any level will form a closed electron shell and produce a noble gas. This is often referred to as the Rule of 8, or the Octet Rule. For the first 8 electrons that go into the third level, from sodium to chlorine, we just see a repeat of the pattern established for the second level. 2 s electrons followed by 6 p electrons. We'll page through them rather quickly. Remember that you can bring up the periodic table at any time and look at the detailed representation of any element. At argon, the third level looks like the second did with neon, with its s and p sublevels containing 2 and 6 electrons respectively. Since the next electron would need to be entered into a new sublevel, argon, with a 1s2, 2s2, 2p6, 3s2, 3p6 electron structure, has a closed shell and is one of the noble gases. This is another example of the rule of 8. 2s electrons plus 6p electrons equals the 8 electrons characteristic of a closed shell. If the electrons were added in strict level order, we would expect that the 3d electrons would come next. But as you just learned, the 3d sublevel is actually higher in energy than the 4s sublevel. So the next electrons to be added will enter the 4s sublevel rather than the 3d. For potassium and calcium, this means that their outermost electrons go into the 4s sublevel. This gives them a similar outer electron configuration to sodium and magnesium, but at the next higher level. Since the 3d sublevel is lower in energy than the 4p, the next electron, in scandium, goes into a 3d orbital. We've entered the first transition element series, a set of 10 elements that show very similar chemical and physical properties, since the two 4s electrons predominate while the 3d sublevel is being filled. Because the properties are so similar, we will show only one other example, chromium, which exhibits the unusual feature of borrowing a 4s electron to produce a half-filled 3d sublevel. According to quantum mechanics, half-filled and completely filled sublevels are energetically favored. Once the 3d sublevel has been filled, we revert to the normal filling of the 4p sublevel, just as occurred with the 2p and 3p sublevels earlier. We'll show only the element at the end of this sequence, the noble gas, krypton. At this point, we've reached another rule of 8 closed shell, although at this point we really should be calling it the rule of 18, since we needed to insert 2 4s electrons, 10 3d electrons, and 6 4p electrons to reach the krypton closed shell. We have both the 4d and 4f sublevels to fill, but their energy is higher than that of the 5s sublevel. In fact, the 4f is even beyond the 6s. As a result, the filling of the 5s, 4d, 5p sublevels follows the same pattern as the 4s, 3d, 4p sublevels we have already seen in row 4. 2 5s electrons, 10 4d electrons, and 6 5p electrons. By the rule of 8, or more properly 18, xenon with its completed 5s and 5p sublevels is a noble gas. However, we still have the 4f, 5d, and 5f sublevels as leftovers from the lower levels yet to be filled. The 4f and 5d are done in row 6. The 5f must wait until row 7. The new feature in row 6 is the filling of the 4f sublevel, an inner transition series that is 14 elements long. As with the other transition series, the chemical and physical properties are determined almost entirely by the two 6s electrons. The 4f orbitals are even more inaccessible than the 5d orbitals. This row continues with the 10 transition series elements that correspond to the filling of the 5d sublevel, followed by the 6p elements and ending with a noble gas, radon. Starting with the 7s orbital at francium, the elements repeat the exact same pattern as with row 6. 2 7s electrons, then 14 5f, 10 6d, and 6 7p. That is, it would happen this way, except that we're running out of elements. The nucleus is getting too big to hold together. Everything past bismuth, atomic number 83, is radioactive. and everything past uranium, atomic number 92, is synthetic. We have just completed a task that would make us the envy of the ancient alchemists. We have created every element in the periodic table. We've seen how electrons are located in levels, sublevels, and orbitals, and how there is a natural progression from orbital to orbital as electrons are added.